Once upon a time, long, long ago in the year 2021, there was a little robot named Shrapnel Mine. It had a fierce saw blade and a front hinge flipper designed to get under its opponents and slice through their underbellies. But no matter how hard it tried, things never quite worked out right. When Shrapnel Mine charged into battle, its saw would whir menacingly, ready to tear into its enemies, but each time it made contact, the blade would just scrape, leaving nothing but a few sad sparks. The forks would often get stuck in the floor, leaving Shrapnel Mine stranded and vulnerable. To make things worse, Shrapnel Mine's battery had a bad habit of dying in the middle of a fight. Each match, it seemed like just when it might have a chance, the robot would slow to a halt, lights flickering out as its energy drained away. After a year of struggles, its creator decided it was time for an upgrade. Shrapnel Mine was given a bigger, stronger battery, and hope was renewed. But with new power came new problems. In its very next fight, the robot charged in with energy like never before, only for its wheels to be easily snapped off by a single blow from its opponent. No matter how many upgrades it caught, Shrapnel Mine never won a single fight. But even as its parts rattled apart and its saw sputtered out, Shrapnel Mine never gave up. It knew that one day it would finally land that perfect slice, or at least try its best until the very end. For the past 2 years, Shrapnel Mine was enshrined in the display case just behind. What remained of it sat, biding its time. But it calls to me. Now, I can be alive once more. You have the technology. You've developed new components, the perfect ones to make a better, faster, stronger Shrapnel Mine. Maybe even one that can get the perfect slice. But our story today doesn't begin with this version of the robot, but instead with this one.
This video is sponsored by PCBWay.
Hey there, this is Seth Schaefer from Team Just 'Cause Robotics. Hope you guys liked that intro. Let me know in the comments how you felt about it. But anyway, today's video is going to be about the development cycle for the brand new Shrapnel Mine version 2, and how I went from trying to make something like this to something like this. And mostly I'll be focusing in this video on the flywheel flipper mechanism that I tried to make work, because that was what I started out with trying to make Shrapnel Mine V2 into. My goal was to basically launch robots into the ceiling repeatedly during a fight, but I ran into a lot of problems down this design path, which I'll go over in this video. And then in the next video, I will give a design overview of what actually became the physical construction of the robot that just competed on Saturday, which is this one here. The punching spinner system was obviously the main feature of this version of the bot, and I'll talk about how I came to the conclusion that that would be a better approach in the next one. And then, of course, I will have a full event recap for how the robot did at the competition in the third video that will hopefully be out in about a month, maybe a month and a half from now. I'm going to hope to try and get the next 3 videos out like 1 or 2 weeks apart, so we will see how I do with staying on schedule with that. I'm very busy running a whole company by myself in all of the time I don't spend on YouTube, so it can be quite difficult to get videos out in a timely manner. So what the heck is Shrapnel Mine anyway? Well, Shrapnel Mine is a 3-pound combat robot that I designed and built for the 2021 Sword event. So this robot has been around for quite a while, but it's only actually competed 2 times. Once at that 2021 event, the recap from which became the most viewed video on my channel for some reason, with over 45,000 views. Not much in the grand scheme of YouTube, but a lot for my channel where most of my videos get less than 5,000 views. So Shrapnel Mine was a successful video idea, but not a very successful robot design. Let me show you. This is what's left of that version of the robot. It's pretty much the same as the first version, except that I added this steel wedge on the front as an option to fight horizontal spinners, and there's supposed to be a motor with a blade right here. The main difference between version 1 and version 2 of the bot was that I upgraded the power system from 2 cells to 4 cells, and I refined a lot of the different mechanical systems in the bot for the drive system a little bit, but ultimately it was pretty much the same as what you see here. The main idea was there was a spinning saw blade up here, and as I pushed an opponent up against a wall, I could kind of pivot them so that their bottom was facing the spinner, and then drive the spinner into their underside, which is usually the least armored part of my opponents. This front hinged flipper plus servo arm combo was kind of complicated and fragile though, I beefed it up a ton more than I needed to, and it ended up making the front of the robot super heavy, and with the wheels in the back, it never really drove that well because the weight distribution was so poor. A control robot really benefits from having more than 2 wheels, I've found in most cases, so when redesigning the bot, I definitely wanted it to be 4-wheel drive. But I also wanted a completely different weapon system because this one didn't really serve its purpose all that well. When you push an opponent against a wall and try to saw through the underside, you're completely limited in how much pressure you can apply with that saw blade by the amount of traction the drivetrain can get. And with all the weight in the front and the wheels in the back, that was not very much. So it didn't really do a whole lot to opponents that weren't made of literal cardboard and tape, which thankfully at least one of its opponents was. My last video, released about a month ago, was about how to design a combat robot kinetic energy spinner weapon system. And in that video, I talked about the importance of a bite to deliver all the energy that your spinning weapon can carry. With Shrapnel Mine's design, I had a 6-toothed blade that was kind of a combination between a saw that cuts and a blade that impacts the opponent, but it was kind of the worst of both worlds. So when I redesigned the bot, I knew that I was going to need fewer impactors and a way to deliver energy a lot more efficiently. This kind of led me down a completely different path, which was the idea of a flywheel flipper. The whole concept behind a flywheel flipper robot is that you spin up a flywheel to store kinetic energy, and then you dump it into your opponent 100% at once by having an arm that just launches them into the air and makes their whole robot hit the ceiling or something like that. I thought it would be really, really cool to be able to put on entertaining fights where you could consistently throw an opponent into the ceiling multiple times per match. And even though it's a completely different type of weapon than the kinetic energy delivering or saw blade cutting actions that the first Shrapnel Mine could do, I thought it would still be befitting of the name, as the idea of getting under somebody and popping them into the air is very similar to the Shrapnel Mine actual World War II weapon, which was a landmine that popped out of the ground and then exploded, shooting shrapnel everywhere around it when somebody stepped nearby. Now, as far as I know, there are currently 0 examples of working 3-pound combat robots using a flywheel flipping mechanism. The reason for that being that it is really, really hard to do well. Well, I shouldn't say 0. There are 0 that I know of that have actually competed in an event and fought there, but there is one that was designed and built by Aaron Hill, the designer and builder of Blip, which is kind of the inspiration for this whole thing in the first place. Blip, of course, is a 250-pound combat robot with a flywheel flipping mechanism, the complexity and cost of which far exceed anything I'm personally capable of making, but he also made a still very expensive and complicated 3-pound version that was named Moonshot. So this right here is basically as far as Moonshot ever got towards competing in a robot fight. As you can see, it had no actual armor, the battery is just lying on the floor there, but it did have a 4-wheel drive system and a flipping system that could launch a robot pretty damn high up. So, as you can see, there's quite a bit of math involved in trying to make a flywheel flipper as complex as what Aaron Hill has designed. I'll talk about what my approach was and why I tried to make it as simple as physically possible, and exactly how it differs from what Aaron Hill was doing. Well, maybe not exactly how it differs from what Aaron Hill is doing, because I barely understand what Aaron Hill was doing in the first place. But I can tell you some of the key elements that differ from my design versus his. So why didn't I just copy what Aaron Hill did with Moonshot? Have you seen Moonshot? My God, that thing is so insanely complicated, and it uses so many incredibly expensive machined parts using wire EDM, water jetting, and CNC equipment that's way better than what I have access to. And even though I could outsource some stuff to PCBWay, I only have a couple $100 budget for any individual project through them, and there's absolutely no way that that wouldn't be costing me probably more in the thousands of dollars out of pocket to replicate something that complex. On top of all of that, there was a huge amount of effort that went into making Moonshot, and all of that effort just was to make a proof of concept for what would eventually become Blip, an even more expensive, bigger, and more complicated robot. And Moonshot itself never actually competed, so we never got to see if its mechanism was even durable enough to survive combat anyway. Personally, my approach to making a combat robot is always keep it simple stupid, or KISS. The KISS principle has served me well in all of my robot designs so far. Making a flywheel flipper of any kind is already going outside of the box in that department because they tend to be a lot more complicated, and you certainly can make one that's more complicated and still be easily very effective. Well, I say easily, but obviously any kind of flywheel flipper is pretty damn hard, which is why basically no one has made one that worked and competed so far. But anyway, my design idea was to try and minimize the number of actuators and moving parts as much as I possibly could. I wanted to see if I could get away with literally just a flywheel, a motor to spin up the flywheel, a way to engage the arm with the flywheel, and nothing else. So that's how I arrived at this potential solution. I'll talk about why this didn't quite work out and why the simple approach wasn't better in this case later on in this video. But first, let me talk about the design principle behind this. This was like my 12th iteration on this concept. I completely redesigned this from scratch several times in CAD and in real life just to get to here, where I eventually decided it wasn't good enough and had to pivot to something completely different. But ultimately, here's where we ended up. So, like I said, there's only a couple actuators in here. You've got a motor, an Antweight hub motor that you can buy from justcauserobotics.com in this case, powering the flywheel. This would spin in the direction that I would eventually want the arm to rotate. And it spins at up to about 18,000 RPM. So this flywheel is spinning very, very fast. I need to turn that into a very quick, small jerking motion on the arm. So to accomplish that, I have a servo, which is this aluminum looking thing here, driving a 3D printed nylon gear meshed to a 3D printed carbon fiber nylon rack. And that can do that motion right there. Now, when this is retracted all the way, we also have an arm support. This is pretty much all 3D printed and off-the-shelf hardware and bearings. And that would simply go right here and be fixed to the base plate. So now you can see the flywheel would be spinning really fast like this, and then the servo would slowly push, well, hopefully quickly, push the flywheel mechanism into the clutch disc, I call this part, which is bolted directly to the arm, and then the flywheel and arm would spin up together, launching my opponent. However, I ran into a lot of mechanical inefficiencies that I didn't have any way of predicting before I actually built and tested the system in real life. Theory only gets you so far, unfortunately. But let me talk a bit about the theory that arrived me at the conclusion that this might even work in the first place next. And then I'll talk about how I got through various mechanical iterations of trying to build and test in real life and trying to make it a little bit better each time before arriving at, this final solution. Because as we engineers know, no project ever works out perfectly the first time. And it's the journey and things that we try along the way that allow us to learn the process of engineering. And we learn by doing and by failing over and over again and getting slightly better and smarter each time that we do it. All right, I'm going to breeze through this a bit because I can feel my viewer retention dropping by the second as a spreadsheet is shown on screen. But this is the spreadsheet that convinced me that any of this might be even remotely possible in the first place. Essentially, what you're looking at here is a cone clutch calculator that determines what this flywheel should be capable of delivering in terms of torque and energy to this arm. This is the cone in my cone clutch. The cone is also the flywheel in this case, and it has some outer radius and some inner radius, which is also at some angle. Those are three of the terms that you'll see, and those three terms together basically just determine how much surface area should be engaging with the clutch disc, which is what I call this part of the arm, the part that is, attached to the arm. So this clutch disc here should have a completely identical mating surface on the inside to what you see on the outside of the cone. And essentially, the amount of pressure with which the servo can squeeze these two together and that surface area and angle should determine how much torque can be transferred to the arm, and therefore whether it should be possible to actually throw another robot into the air. All the math on this spreadsheet really is doing is saying, for the input values of that particular servo with its current gear ratio and with the specific inner and outer radius and force of friction that I can assume would act between those two parts, and all of the parameters of the flywheel and how much energy is stored in the flywheel, essentially, I have enough energy that if 100% of the mechanical energy stored in the spinning flywheel at 17,000 RPM was transferred into gravitational potential energy of lifting a 3-pound robot up into the air, I should be able to lift this robot 41 feet. In other words, the flywheel has way more than 10 times as much energy as is needed to throw a robot 4 feet in the air into the ceiling of the arena, which was my stated goal. However, there's no way in hell that I would ever transfer anywhere close to 100% of that energy into flipping another robot. And there are a lot of reasons for that, but essentially a ton of that is going to burn off as friction and turn into heat. So as the parts are rubbing together, the cone and the clutch are rubbing together, there's no chance that they instantly lock and deliver full power with no losses. And I fully expected that that would be the case from the start, which is why I was starting with 10 times as much energy as I need in the first place. However, I was hoping that I could basically get the system to be, 8 to 10% efficient, whereas it turns out in reality I could only get it to be like 0.5% to 1% efficient. And this is ultimately why things didn't work the way that I had planned. I had already kind of accounted for the inefficiency to some extent with these calculations here, which are basically saying I can only apply the force over a small distance, which is, how much the arm tip rises, and that can only happen over a particular work distance. And so the energy imparted should be the force at the tip of the arm times the distance over which the arm is applied. And so the maximum energy I could impart based on that calculation is about 13 joules, which is enough to throw a robot, 3.2 feet in the air. I think there are a variety of different things that caused this system to work a lot worse than I anticipated. Number one is this force of friction, I think, is actually way higher than it would be in real life. It's probably more like 0.2 or 0.3 right now because I'm using a brass flywheel, and brass is pretty slippery, and I'm going against a plastic clutch disc, which is also kind of slippery. I actually lined the inside of this particular clutch disc with rubber cement to add more grip and increase that force of friction, but then I ran into problems with all of the other issues, which are not something represented directly on this spreadsheet. What I believe is the biggest cause of problems for me is, number one, the servo can't supply enough force in the direction that I need it to be. So it's not applying force exactly in the center of the flywheel. Obviously, it's applying the force over here. And so that's causing the carriage to kind of tilt, and it wants to bind up when it tilts. And so I'm not delivering the full pressure that I should, and way less pressure than I anticipated. And number two, the bigger limiting factor for how much pressure I can actually apply between the clutch disc and the cone clutch itself is the fact that everything supporting this is all 3D printed plastic. Like, none of this is that rigid, and the forces that should be clamping those two surfaces together perfectly aligned are instead causing them to bend and flex and become misaligned. And if there's even a tiny bit of angular misalignment between the clutch disc and the cone, the amount of surface area that is delivering force to it becomes a tiny, tiny fraction of what it should be. And I believe this is probably the biggest problem that I experienced that led to the system not throwing a robot 3 feet in the air, but rather throwing a robot like 2 or 3 inches in the air. But I couldn't figure out a way to solve all of those problems without this essentially just becoming way too beefy and heavy and large to reasonably fit into a Beetleweight robot. I think that a system like this could be a lot more suitable for a 12 or 30 pound robot, especially because there are several working examples of flywheel flippers in 12 and 30 pound robots. I'd like to thank the sponsor of today's video, PCBWay. PCBWay helped to machine one amazing component for the new Shrapnel Mine. You can see this 7075 aluminum slider carriage right here. They actually made 3 of these, but I forgot to bring 2 of them with me to the event because I was so confident that one of them would last the whole time, and of course there were no problems with it whatsoever. Here is one of the other ones. This is what that piece looks like. It is machined out of billet 7075 aluminum. 4 holes to mount the hub motor, a slot for the hub motor wires, counter bores for the screws to mount to a linear guide carriage, and then 2 more screw holes here that bolt directly to an XL belt that drives the slider. I'll talk more about this in my next video in the design overview of the puncher shrapnel mine. But yeah, this part, fantastic, made out of 7075 aluminum. And if I wanted to get this machined in-house, I was going to be buying a block of 7075 aluminum on a master that actually cost only a tiny bit less than getting 3 of these machined and sent to me from PCBWay would have, which is why I let them do the work for me rather than trying to do it myself with my router, which would have been a huge pain as well. So thank you so much to PCBWay for supporting Just Cause Robotics for such a long time and making awesome parts for me. Make sure to check them out at the link in the description to get $5 off your first order. PCB fabrication, 3D printing, or CNC machining in all kinds of awesome materials. So that leads us to how I pivoted to making a robot like this instead. But you'll have to subscribe and hit the bell so you get notified when that video comes out in a couple weeks, because I have lots of other stuff to work on today, and this video's already gotten quite long. So make sure to like if you enjoyed this video, and let me know in the comments if you have suggestions for how I could have made the flywheel flipper system work a lot better. All right, that's all I've got for you today. Thank you so much for watching.